So what would be one answer that you came up with? Anybody?
It's like 175 feet.
175 feet. Somebody else? 195 feet.
230.
230 feet. Okay? Those are all in the, I mean, there's pretty good range there. Okay, Spencer, first 175. Tell us what you're thinking there.
I used an equation for one-dimensional kinematics.
Okay, and that was what?
The initial velocity plus the final velocity divided by 2 and multiply all that by the time it's taken.
Okay, so fancy way of saying a physics formula, right? Kinematics, study of motion. So here we have original velocity of 20, final velocity of 50. Average those is 35. So that's an average of 35 feet per second over a 5-second interval. 35 times 5 is 175. Okay? Keaton, 195.
Okay, so we thought that 0 to 1 it has to have an average velocity of 25 feet per second, and then let's do the average between both of them. So 25 or 35.
25
plus 34 plus 41 plus 46 plus
49. So every second, so it's kind of the same thing that he did, right? Just 5 different times, right? Do the average, so here'd be your original and your final velocity here, and do the average over a 1-second interval. 25, and that doesn't add up the same though, does it? Now that's interesting. Why wouldn't that add up the same? Right. Okay, there's the key, a linear. Physics formula, well, and actually both formulas you guys use are the same formula. Original plus final divided by 2, that's your average, and then times the width of the interval. That assumes a linear velocity, which is a constant acceleration. All physics formulas are based on, all high school physics formulas are based on constant acceleration. Does this problem have constant acceleration? No. It's speeding up faster in the beginning than it is towards the end, right? So both of those are reasonable answers, okay? I would say the 195 might be closer to the actual distance just because you did multiple averages, so you took out that linear piece, and we're going to look at this graphically because I think one person in the other class thought of doing a graph. I think that's the best way to really understand this, is to think of a graph. And what, Cody, what about the 230? Added them all up, and it added up to 230. Well, yeah, now I can see, because what he's saying, here's the only reason that's a little bit too big, but let's think about the idea. 20 feet per second for 1 second goes how far? 20 feet. And 30 feet per second for 1 second goes 30 feet, right? I mean, so it's not without merit. What you're saying is not without merit. 38 feet per second for 1 second is 38. You add them all up. Now the problem is, how many numbers is that? That's actually 6 numbers. So, but how many seconds is this interval? It's only a 5-second interval. So another way of thinking of that might be this. So here's where all these different assumptions come into play now. Let's assume that when the car passed our starting point, it was 20 feet per second, but instantly went to 30. So was it ever going 20 during our time interval? No, just right at the beginning, but then it instantly went to 30, which physically would be really hard to do, but let's just say that's what happened. So if we ignored the 20 and then added them up, right, we would get 210. Now that would be kind of a farthest case scenario, right? That during each second, it was actually traveling its fastest at that whole second. Now, what if it was the other way around? What if it went 20 this whole first second, and then right at the end, it jumped to 30? Then we would take off the 50, and then we would just add up these, right? And that would be 180, right? That'd be kind of the lowest case scenario. Now think about that. The lowest case scenario is 180. The upper end would have been 210. And what's the average between those two? 195. There's a connection between those two numbers right there. Now, let's look at all of this graphically. And we did this the second or third day of class, if you remember. Some of you probably already knew where I was headed with this. Here is a plotting of those 6 points. I have drawn this not with a line, but with a smooth curve. Now, that's an assumption. I don't know if the car was, well, okay. Okay, I made an assumption that this car was smoothly accelerating, not in a linear fashion. Those would have been line segments in between. So let's say it was a curve. Now, what is a connection we learned like the third day of class? If this is velocity, what did we do? Remember? The area underneath of it, right? We talked about this area. Now, I have no idea what this area is because this is a curved shape. It's not a circle. It's not anything we have a geometry formula for. So one way of doing it, I'll do this in red, would be Spencer's idea. Now, I think this would be the description here of Spencer's idea, which would have been to find this area right here. Isn't that true? This trapezoid, because the assumption he made is this was a linear thing from the beginning to the ending velocity, and that's what the physics formula does. Now this makes a trapezoid. Now let's look at the trapezoid formula. 1/2 sum of the bases times the height. Now this is a trapezoid that's turned up on its end. So the bases are actually here, and the height is actually this down here. And all throughout these area problems that we do, that's the kind of trapezoids we'll be talking about. Okay, so it's a trapezoid turned up on its end. The height of the trapezoid is actually down here, and these are the 2 bases. Well, what is this? This is 20. This is 50. So the formula would be 1/2 20 plus 50 times 5. Oh, isn't that what you said you were doing? Isn't this the average of the, I mean, this trapezoid formula is, that's cool, isn't it? This is essentially original velocity plus final velocity divided by 2, and then times that. And then think about what the units are. 20 and 50 are both feet per second, and then the 5 is seconds. And so when we take feet per second times seconds, we get feet. And so this area truly is the distance traveled. Now, we decided that that was a little too low, probably. Well, it certainly looks like it in our graph, right? Because we're missing all this area, right? We think the distance this car traveled would be the area below here. Now, if this truly was a smooth acceleration and this was curved, then what about Keaton's idea?
Smaller trapezoids.
All he did was break it up into smaller trapezoids, but still assuming that between here it was linear, right? So what do you think about the 195 answer?
Better.
Closer, but
Not good enough.
still small, still a little small, because this is curved concave up. It's a little bit over the top of those lines. So those individual trapezoids, this would be 25, this would be 34, and so forth and so on. Those individual trapezoids would add up to 195. Better answer, but still a little bit below. Now let's talk about Cody's idea with the 230. And, well, actually, I changed a little bit to 210, right? What would it look like if the car, when it first hit that point, jumped right to 30 right away? Wouldn't that be that?
Yeah.
That would be a rectangle. 30. And then it jumped up to here. Whoops. Jumped up to here. 38. Then jumped up to here. Right? That's what that would be. And what would the last one have been? The last one would have been up here at a height of 50 and so forth. So we would not have used the 20. Notice this number we didn't use. We started here with the 30. We used those. We didn't use the left edge. Those have a name. Those are called right endpoint rectangles. And we'll get into that later in the chapter. Those are right endpoint rectangles. Now, those are clearly an over-approximation of the area. Right? Now, the other answer I said was, what if, we'll do green here, what if the car stayed 20 the whole first second? Now you would have that rectangle, or that rectangle, or that rectangle. And would we use the 50? No, because the last rectangle would have been right here. Now that's clearly under. Now what if you took the blue and the yellow or greenish rectangles? and average them. Wouldn't you get the red trapezoid? And that's really what a trapezoid is, actually. A trapezoid here is really an average between that rectangle and that rectangle. And of course, we saw how a trapezoid really is an average. This half to base 1 plus base 2 is really an average of the two bases. And it's turning it into a rectangle is what it's doing. A rectangle is base times height. This is saying average the bases times the height. That's what a trapezoid is. So we've got those rectangles, we've got that trapezoid, so we can see how 180, 210, average 195. All right, that's a lot of stuff, but the most important part of that, some of that we'll come back and revisit. The most important part of this, hopefully, is a motivation. Not that you need any motivation, but hopefully it's a motivation, again, to piggyback off of what I tried to give you the third day of class, a motivation of why we might be interested in the area underneath a curve. In this case, the area under a velocity curve. Because it tells us the position, it tells us some information. Just like slope, the motivation was the slope of a line gave us the rate of change. And then we learned in chapter 4 all the different applications, all the different uses we could get from derivative. Related to rate problems, optimization problems, all those different kinds of things. Okay? Well, the same thing is going to happen here. We're going to take this idea that area under the curve gives us something, some information that could be useful. And we're going to see where that leads us, okay? So now, what we need to do is take a step back and say, okay, so if it's useful to talk about the area under a curve, let's get some notation, right? So really, we're kind of going back to what we did at the beginning of the year, and the way we build this is going to be very similar to how we did it before, so we should be able to go a little faster. It should make more sense because it's not the first time you've seen this. The strategies we employ are going to seem very, very familiar, all right? So let's take a look at that calculator thing that I sent to you. All right, so everybody, when you opened it up, did it open to this page right here? And did it look like this? I can't remember. I think when I send it, it sends it just the way I have it when it's open. But I might be wrong. It's called definite integral. It didn't open to 1.2. So when you go to 1.2, though, does it look just like this? And this says curly thing 0 to 1.42, right? Okay. The curly thing is the symbol for an integral. Okay? And like the name of this thing calls, it's a definite integral. Now we're going to write that in our notes here in a second. Okay? And notice what we have right here. Okay? We got this shaded piece because we've talked about how it might be interesting and useful to find the area underneath a curve. And so we've got this shaded piece here. Down here it's telling us that that area is 1.42. Okay, seems reasonable. Here's a box that would be 1, and this looks like it's about half. So that seems reasonable. Notice we have the 0 and the 2 here. Well, look at my left endpoint is 0. My right endpoint over here is 2. That's what those numbers are. Notice that this number down here is the littler number. It's on the bottom. Bigger numbers on the top. 99% of the time when we write an integral, that's how we want to write it. That's the normal way of writing an integral. Littler number down here, bigger number up here. If we were to write that backwards, then our area would be opposite. And we'll talk about what that means as far as opposite here in a second. Okay? So now, the purpose of giving you this document is to let you slide these things around and play with some things. I just told you that if these were written backwards, that the area would be opposite. Okay? And what about this idea of this part of the curve over here? What about the part of the curve that's below the x-axis? So here's what I want you to do. I want you to drag the A, and you can do that by just control-clicking, or you can just click and hold on the A, and then drag to the left. I think you can click and hold until the fist closes, I think. And then you can just, with your finger, you can just, on the trackpad, move that to the left. Let's move that A over to the left. Then let's grab the B, and let's slide that over there as well. Okay, mine is not going to do. just gonna say if yours won't work, you can just look on mine, but now mine's not working. Okay, let me try control clicking. Oh, man. There it goes. Fine. All right. Now, are you able to do that on yours? I mean, if not, it's not the end of the world. You can look up here. But now, notice the integral from a to b, negative 2.5 to negative 0.9. Now, notice what you see with the area right there. It's negative. Now, notice the term area under the curve is kind of misleading. It's the term that calculus books have always used, though. It's really the area between the curve and the x-axis, right? To me, that area looks like it's above the curve. So to say under the curve seems kind of confusing, okay? So what we really mean, and I'll slip and I'll say it, what we really mean when we do area under curve is area between the curve and the x-axis, always. We never do this area down here that would go forever, it'd be infinite. So it's the area between the curve and the x-axis. It's negative, so area below is negative, area above is positive, very simple. You'd say, well, how can you have a negative area? Well, because remember, we're talking about distance. And remember how we thought if you go east of Bismarck, that's positive. And if you go west of Bismarck, that's negative. It's like displacement. It's like displacement. Okay? Now, watch what happens if I bring B now back to the right. At some point, look at my area is 0. Right? Well, then that makes sense. I got this negative area over here canceling out this positive area. Again, like displacement. So that would be like going east for 10 miles and coming back west for 10 miles. I'm back at my starting point. Okay? That kind of thing is what would be going on. Again, think about this as a velocity graph. So the velocity over here would be negative, means going left, and the velocity here is positive, which means going right. And so now you're back where you start. Okay? This is an odd function. Has origin symmetry. Look at my integral, negative 2.5 to 2.5. So it makes sense that this area would cancel out that area. All right, now, let's bring that A all the way over here past the B. Now again, I told you that normal integrals, the integral from A to B, the A is to the left of the B. The bottom number is smaller than this top number. But if an integral would be written backwards, like this one, the 4.3 is on the bottom, the 2.5 is on the top. Notice what happened to the area. It's opposite. So here I've got area that's above the x-axis, which should be positive, but since my integral was written backwards, it's opposite. So that becomes a negative area. Now, why would you write it backwards? Well, you'll see there are some problems where it just happens. It's not because we did it on purpose to try to be tricky. It just, in the setup of the problem, it happens to end up that way. So we just need to know that that is the case. We'll write that down as a formula here in our notes here in a minute. Okay? So those are the main things that we have about area. And this new curly thing, this curly notation. All right? It's just the integral symbol. That's it. Yeah, that's as good as it gets. So okay, so here we go. So here is our definition of a definite integral. Just like when we defined the derivative. When we defined y prime, we just said it's the slope of the tangent line to a curve. Now we gave a formal definition later, the f of x plus h minus f of x, and we're going to do that with this as well. We're going to have a more formal definition later, but for now, we're just going to say a definite integral. And definite means you're going to see there's going to be something called an indefinite integral later. So a definite integral means a defined piece of area from a to b. And notice how we write it. The function goes in here. And this dx just means the same thing it did with derivative, with respect to x. This would be equivalent to the Leibniz notation. I'll put it over here. This would be the equivalent of writing this. when we learned about derivative. Now, we went right to the f prime notation, but that would be the equivalent. The derivative with respect to x of f of x. This is the integral of f of x with respect to x. But we do want to tack that dx on there. We do want to have that sticking on the end. Now, later it'll come to have a little more important meaning for us. Okay, but for right now, we just put it there and we say, hey, that's with respect to x. So if our function was t, that'd be dt. Okay, just like we've been doing. And here's just a picture of what that means. Area between the function and the x-axis. All right, now, your homework is going to be some problems where you're going to find some areas. Okay, you'll be given certain information about it, and you're going to be able to find those areas. Okay, now, where do we start with that? Well, the first types of areas we know how to find are geometry areas. Rectangles, trapezoids, triangles, circles. All right, so you may get some problems where they just give you a graph, something like this. Here's a function. Now, it's just a piecewise function, but it's made up of lines and circles, so that way you get triangles and trapezoids and stuff like that. So if you were given a formula or a graph like this and asked to find some areas, you would just use geometry to do it. Okay, so let's say you were asked to do the area from A to B. In this case, -5, man, it's slow. I got all these things open, I'm recording. Crazy. All right. What's that area? 3 by 2, and it's below the x-axis, so -6. Right? If you were asked to do the area from B to C, what's your guess? 0. This triangle is the same as this triangle. That's a 3 by 2, so that'd be 6 times a half is 3. This would be -3. This would be +3. We get an area of 0 because some's positive, some's negative. Okay, if you're going to go from C to D, split it into 2. You got a rectangle down here, which would be 4 by 2. That's 8. And then you've got a circle that's a half a circle. Pi r squared, radius 2, that'd be 4 pi. Half of that is 2 pi, so 8 plus 2 pi. Right? And then the last one, D to E, would be a trapezoid. Okay, and that trapezoid would be an area of 3. So those should be simple, just some geometry type stuff. Okay, now remember, if you go backwards, if they ask for the integral from E to D, if it says from 9 to 7, that's backwards. So then this area ends up being -3, right? If it's above the x-axis, it's normally positive, but if your integral's backwards, where these numbers are, then it's opposite. Okay? Likewise, if I go from B to A, okay, normally this area down here would be negative. But since my integral is going from -2 to -5, it's going backwards, this actually becomes a positive area. Okay? So that's one thing. Now, I might also give that, instead of as a graph, I might give you that problem like this. Oops. Okay, I might give you this problem. Let's go ahead and write this one down. Let's say I gave you the integral from 2 to 5 of absolute value of x minus 1 dx. And I wanted you to find this area. When you read this, you should, for right now, you read that as, okay, that's an area. It's a number answer, right? Just like when I asked you to find the slope, the derivative at 2, it's a number answer because it's a slope at 2. Well, this is the area under this curve from 2 to 5. So what's your strategy going to be? Graph it, absolutely. I mean, that's really our only strategy, and why I didn't draw that on my grid, I have no idea. That's why I have the grid up there. So we would maybe that's why I didn't do it, because I can't follow the lines anyway. All right, so what would this graph look like? V shifted 1 to the right. Oh boy, we're in trouble. It's the V graph shifted 1 to the right. So the area from 2 to 5 would be this area right here, wouldn't it? Now, that's a line, so that makes a trapezoid. So in other words, I might give you some equations that you can actually graph, and then when you graph them, they will create shapes that are geometric shapes that you can just find that area. So that's a trapezoid. Now, if you want to split that into a rectangle and a triangle, you can. If you just want to count squares, you could. But as a trapezoid, this would be a 1 here and a what? 4 here. So that'd be 1/2, 1 plus 4, times a height of 3. So that'd be 5/2 times 3, which would be 15/2. And don't make it a decimal. Don't, whoops. 2. So that'd be 15/2. Right? Just leave it as that. That's fine. Okay? So something like that. So that shouldn't be that hard. All right, then, the last thing that's going to be on there is going to be, on your homework, is going to be to take advantage of some basic rules of integrals that we're going to just go over real quickly here. If I have the integral of a function like this, okay, where I have a function plus or minus a function, I can split that into 2 separate integrals. That's just like derivatives. Remember, we had that rule for derivatives. If I have a function plus a function, if I have x squared plus sine x, and I want to do the derivative, I can do the derivative of each piece. Now, I can't do that with product and quotient, though. That's why we had the product and quotient rules. The same thing applies here. If I've got x squared times sine x, I can't do the area under x squared and the area under sine and the multiply. I can't do that. Okay? But if I'm adding or subtracting 2 functions, I can split that into 2 separate integrals. Okay? Now, why would that be helpful? Well, actually, let me give you one more rule first. Let me give you this top one. Boy, this is okay, let me give you this top rule here as well. Then we'll use both those rules together. And I'll give you an example of a problem that you could do with it. So this says if you have a constant setting in front of a function. Now, what have we learned in derivatives? If you have a constant setting in front, how does that affect the derivative? It just sets out there, and then you do the derivative. Well, the same thing's true here. If you have a constant in front of a function, you can just pull that constant out in front of the integral, and then you can do your area, and then tack on that constant. Well, that makes sense, because if you take a constant times a function, it just stretches the graph. What do you suppose that does to the area? Stretches it just as much. So in other words, if you have a 2 in front of a function, it makes the graph twice as tall. Well, that's going to give you twice as much area, right? It's twice as tall. So it's going to make the area twice as much. So we can just pull the constant out in front. Okay? So let's take those 2 formulas and let me show you a problem you could do. So let's say in the directions they told you this. The integral from 2 to 4 of x squared dx is 10. Now it's not, but let's just pretend. Okay? So in the directions they told you that. Now, why did they have to tell you that? Well, because we could not find that area. Think about the graph of x squared. If you went from 2 to 4, could you find that area? Why not? It's curved. There's no geometry formula. That's not a trapezoid. It's curved. And we don't know how to find it. Now, we're going to learn how to find it, but we don't know how to find that right now. Okay? So, we don't know what that area is. I know it'd be positive something. Okay? But they're telling me it's 10. Okay, so let's say to that. All right, so now, the problem they're going to give you is this. They're going to give you that problem right there and ask you to find that area. Okay? So, what we do is we use those 2 laws that we just learned, which is first I can split this apart. into this integral plus this integral. Okay? Now what can I do with that first integral? I can put the 3 out in front. Right? Now, what is that then? That's just 3 times 10. Right? Because they told me that this integral of x squared dx is 10. So 3 times 10 is 30. Okay, now what about this integral here? I say that we could draw that, right? That is the function y equals 2. So that is a horizontal line up here at 2, and we want the area from 2 to 4. So what's that going to be? 4, right? It's too tall and too wide. So this right here, now if that would have been a 2x, we could have done that also, because we could have drawn the line y equals 2x, and we'd have had a triangle, right? So it would have been, so what happens is, a function like this, we say, oh, that's curved. We don't know how to do that. Unless it makes a circle or a triangle or a trapezoid, right now we don't know how to find the area unless they're geometry shapes. This wouldn't be a geometry shape, so that's why they told me that. But here, this makes a geometry shape. I graph the line y equals 2 from 2 to 4. That would have an area of 4. So this would be 30 plus 4, 34. So the answer to this problem, the answer to this integral right here, is 34. Okay? So we can take advantage of those two properties that we just learned about splitting apart an integral and about pulling the constant out in front to do some stuff and work with this notation. All right. The last thing then is this formula down here at the bottom. And this formula says, here I've got a picture from A to B, and I've got C in between. This says the integral from A to B, the area from A to B, is equal to the area from A to C plus the area from C to B. Earth-shattering? Not really. But, and you'll see this, I think, maybe in some of the homework. It might not come till tomorrow's homework. I think it's going to be in some of today's homework. The interesting, the cool thing about this, not necessarily earth-shattering, but this formula works even if C is not between the A and the B. It makes perfect sense when the C is in between. But move the C out here, past the B, and this is still true. And so you'll get to work with that a little bit, and we'll talk about that some more. Okay, so it is kind of an important formula. All right? Okay, so your homework is in section 5.1, and you got time to get started here a little bit.
I know that when we were in chapter 4, I was like, this isn't.
All right, so we are going to do the top line up to number 36.
Still.
Okay? The top line up to number 36. Now, welcome back, right? We've got, we've been doing packet stuff, and for some of you that's not been, well, I don't know, but, right, we haven't done a lot of new stuff, right? We've got to get back into routine here a little bit. So the first line up to number 36. For tomorrow.